And we are recording. So this is Mech 2, Group 2, Helios. So let me get out of the way and let them share their heliostat design.
All right. Good afternoon. We hope everyone is doing well. Thank you for taking the time to join us for our final heliostat design presentation. We look forward to hearing your feedback at the end of this presentation. So we are Helios, which besides being the name of the ancient Greek god of the sun, stands for High Efficiency Light Intensifying Optical System. Our team, Group 2, consists of 7 mechanical engineers. Myself, Ryan Flickinger, as well as
Alex Odozbol.
Dario Calle.
Derek Cologne.
Chloe Grew.
Rachel Jones.
Ethan, you there?
All hear me? I'm so sorry.
Okay.
I'm Ethan Lasang. Thanks for being here.
Okay, so our presentation will begin with our core values and motivations that help guide our design process. Next, we will go into a general product overview to help establish some familiarity with our solution. We will then briefly touch on the field layout for our product if it was going to be implemented on a large scale. Then a breakdown and analysis of our 5 critical subsystems will follow. These subsystems are the base, the support frame, the rotation mechanism, the reflection surface, and lastly, the system control subsystem. Next, we will highlight the key features of our design that make it unique, and then move into detailing the assembly time for our module. After that, we will cover our product's cost breakdown, and lastly, we will move into our summary and conclusion. First up, our core values.
Brian, could you speak up or turn up your mic a bit? It's really hard to hear you relative to everyone else.
Yes, ma'am. So, as a group, we shared a passion with addressing the world's growing energy crisis. We aim to reduce the heavy demand on fossil fuels by offering a system that was renewable, affordable, and sustainable. Our strengths and interests within the engineering discipline varied widely, which allowed for a collaborative effort where each team member was able to work within their individual strengths. This approach allowed for the development of a unique solution, which we believe best suits our customers' needs. The Helios product fits into the energy market by fulfilling a need to reduce the cost of renewable energy sources, which in turn facilitates an increase in energy independence. To help familiarize you with our product, here's a general overview. The base subsystem is 4 feet of angle aluminum set in the ground in a 6-inch diameter cylindrical core of concrete to a depth of 18 inches. The support frame subsystem is constructed from 2-inch PVC pipe and fittings. There are 4 interior sections of 3/4-inch PVC pipe that serve to hold the reflective surfaces in place. For reflector rotation, there are stepper motors mounted inside the pipe fittings, which in turn spin these 3/4-inch pipes to grant each reflector an individual axis of rotation. The reflection surface subsystem consists of 4 square pieces of float glass, each having an area of 1/4 meter squared and measuring 1 centimeter thick. These are adhered to the previously mentioned 3/4-inch PVC pipe. For azimuthal rotation, a planetary gear system is used to rotate the frame about the base's vertical axis. This relies on a NEMA 17 400 step motor to directly drive one of the planet gears in this 3-planet system. Solar tracking is performed by an ESP32 controller in conjunction with 5 NEMA 17 motor drivers. These motor drivers are used to half-step all 5 motors in our heliostat. I will now hand it over to my partner, Ethan.
Small-scale heliostat technology by maintaining a small footprint relative to the reflection area of 1 square meter, with a size ratio of 2.14 when compared with the projected area of the clear PVC support frame. The overall design is composed of the previously highlighted 5 critical subsystems: the base, support frame, reflection surface, rotation mechanisms, and solar tracking systems, with the sum of these components being a lightweight and effective design that can be prototyped for $663.85 and mass-produced for a solar field of 1,688 modules at $164.80 per square meter. And now for an animation of the azimuthal rotation of the frame followed by an animation of the reflection surface rotation.
So before we discuss design details of the heliostat, I would like to show the field layout that we have chosen for this design. So this field design utilizes a cornfield layout and assumes that the receiver is planar. This is opposed to a cylindrical receiver, which would require more heliostats in the south and eastern fields. So the field shown here in this slide was generated using a program called Solar Pilot, and the field was optimized to contain 1,688 modules at a latitude of 36 degrees north, which is Las Vegas. So the field occupies 2.65 acres, with the majority of the reflectors being in the north field, with a slight bias towards the east field, as you can see. The way that the reflectors are organized, red are the most efficient, and then as it gets to blue, those are the least efficient in the field. So the reflector locations in the current orientation were, again, based on the most efficient. So as we narrowed it down to 1,688, more were taken out of the east and western fields of the heliostat array. So the furthest heliostat is 100 meters away, while the closest module is 20 meters away. The cornfield layout was chosen over a staggered radial pattern because it allows for minimized shading between modules and maximized efficiency for heliostats that are near the receiver. So the reason why they aren't closer to the receiver is because, again, the closer they are, the less efficient. So 20 meters was kind of a sweet spot for us. So next, I will cover the base subsystem. So the base subsystem is simple, lightweight, and inexpensive. Assembly cost and time is minimized through the use of a few simple components. These components include 4 feet of 2-inch 6061 aluminum angle stock, 1 foot of 3/8 threaded 6061 aluminum threaded rod, a section of 10 gauge 6061 aluminum sheet metal, a poured concrete base, NEMA 17 stepper motor as well to deal with rotation. So to assemble the base, the bottom 18 inches of the angle stock are set into Portland concrete, and then this concrete section is then buried into the ground. Then the bottom 4 inches of the threaded rod are TIG welded onto the internal section of the angle stock. The 10 gauge motor mount aluminum sheet metal is then TIG welded to the top of the angle stock. And then, of course, the motor can be mounted onto the bottom of the 10 gauge. So I guess next I will start going over some of the bending stress calculations. So there were 2 loading conditions that were considered for bending stress. The first case considers 140 mile/hour winds, which applies a factor of safety of 2 to the maximum wind speed of 70 miles per hour. This case assumes that the field was prepared beforehand and that the reflectors are parallel to the ground. This orientation ensures that wind load is minimized. The second case considers 30 mile/hour wind gusts, and this case assumes that the field was not prepared beforehand and that the reflectors are perpendicular to the ground. This will, again, maximize the wind load on those reflectors. So the bending of the aluminum angle stock is not considered, and it is assumed to be completely rigid for this case. This is the worst case scenario. So we're specifically treating the aluminum threaded rod as an 8-inch cantilever beam for simplicity, with distributed loads from the top of the frame and the rotation mechanism at the bottom of the frame. The yield strength of the 6061 aluminum is 276 megapascals. The maximum moment applied to the threaded rod during the case forward prepared is 10.235 Newton meters, while the maximum moment in the unprepared case is 4.155 Newton meters. And both of these moments are applied just above where the angle stock meets the top or the bottom of the threaded rod. So the bending stress on the threaded rod during the prepared case is 120.6 megapascals, while the bending stress applied during the unprepared case is 49 megapascals. So the yield factor of safety for the prepared case is 2.3, while the yield factor of safety in the unprepared case is 5.6. So 140-mile-per-hour winds are obviously not expected at this site. So again, we factored in that, we assumed 70 miles per hour was our peak, and then we factored in that factor of safety of 2, because that's a customer need right in there, because that was the one, loading case that would have obviously the lower factor of safety. So an additional loading case that was considered for the aluminum threaded rod was an axial fatigue case. So it's in the case of vortex shitting, when air flows over our cylindrical pipe, it creates vortices on the opposite side of the pipe, which causes vertical oscillation of our frame. So this vortex shedding causes the largest forces when the air is the densest. And in this case, that's at nighttime when our air temperature is -6 degrees Celsius. And we're also assuming a 140 mile per hour winds to maximize shedding forces. So the shedding forces using the equation on the right there end up being plus or minus 156.07 newtons, which on the threaded rod applies an axial stress of 2.19 megapascals. The modified endurance limit of the threaded rod is 115.35 megapascals. That's just including surface and loading factor or Marin factors. Obviously, size factor isn't important because it's an axial loading condition. This means that the Goodman factor of safety is 38.4, which strictly means that this is infinite life and nothing more. So next, I will go over some weld failure calculations. So there are 2 welds present in the base subsystem, but the weld that is of the greatest importance is obviously the one connecting the threaded rod to the angle stock. The other one is the 10 gauge plate, and that one only supports the weight of the motor, so we are neglecting that for now. So both the material, the threaded rod and the angle stock, use 6061 aluminum. Welding aluminum is not ideal and it's difficult to perform due to heat resistant oxide layers. So tungsten inert gas or TIG welding is used, and that will be used for the fillet welds on the threaded rod. This welding method is better for maintaining workpiece temperature and is optimal for welding sheet metal. So the applied shear was calculated by finding the throat area of the fillet welds here, which was found to be 68.4 millimeters squared. And the applied load from the frame is 300 newtons. So over that throat area results in 4.387 megapascals of shear. The allowable shear is 124 megapascals, assuming that we used one of the worst electrodes for this application, one of the weakest, which is E60 series. And that gives us a factor of safety of 28.3. So this weld should be safe, and we are safe to use stronger electrodes as well, obviously, to drive down price a little bit. All right. And that's all for welds.
So fatigue analysis was also performed for the 3/8" aluminum threaded rod for bending stress caused from the 140 mile per hour wind force, which, like Derek said, is the maximum wind speed that the heliostat will endure. The maximum bending stress was previously calculated as 120.6 megapascals, and the minimum bending stress is 0. And so from here, the mean and alternating stresses were both calculated as 60.3 megapascals. And since the threaded rod does not experience a fully reverse stress, this was calculated using the alternating stress, the mean stress, and the ultimate tensile strength of the material. So from here, a fatigue factor of safety was calculated using the Gerber failure criteria, and this was calculated as 2.07. And since this factor of safety is greater than 2, this meets customer need 13 of requiring a factor of safety over 2. And an SN diagram was also created for the threaded rod using the ultimate tensile strength and the fully corrected endurance limit to evaluate how it will perform throughout its life cycle.
To go over the support frame. The frame is composed of nearly entirely off-the-shelf components, being Schedule 42-inch PVC and its connectors to reduce costs and allow for rapid prototyping and assembly. There are 4 types of PVC connectors used in the frame: 3 T connectors, 6 4-way crosses, the outer 4 of which are the reflector rotation subassemblies, 4 90-degree angle connectors, and a 2 to 4 inch expander to house the planetary gears and adapt the support frame to the base. Part alterations and custom parts were included sparingly and with the sole purpose of improving subsystem synergy or system function overall to meet customer needs, such as the thrust-bearing engagement surface, drilled hole in the central T to mate with the 3/8 inch threaded rod, and access holes in the bottom of the crosses to insert set screws. The area of most concern within the support frame was the small length of PVC pipe connecting the frame to the planetary gear system of the base. The maximum stress on this section of pipe was found by considering the torsional strain from the motor responsible for azimuthal rotation, the bending stress due to drag force, and the compressive stress due to the weight of the frame, reflectors, and motors. The maximum moment on the pipe is the drag load on the frame multiplied by the length of the base subsystem. The drag force on each reflector, assuming the worst case scenario of the reflectors being angled at 90 degrees and perpendicular to the wind direction, is 252 newtons for a total wind load of 1,008 newtons, while the length of the angle stock base is 0.762 meters. This results in a maximum moment on the pipe of 768.096 Newton meters. With the second area moment of inertia of the PVC pipe calculated as 2.91 times 10 to the minus 7th meters, causing a bending stress of 0.5044 megapascals. Sorry, is that any better? The weight of the frame, motors, and reflectors supported by the pipe is equal to 183.37 newtons, causing compressive stress of 0.2495 megapascals. Torque on the PVC pipe due to the planetary gear motor is 0.55 Newton meters, and the polar moment of inertia was calculated as 5.83 times 10 to the minus 7th meters to the 4th, causing a torsional stress of 0.0284 megapascals. These values were used to calculate the von Mises stress with a simplified form of the equation displayed above, equaling 0.4396 megapascals. The part was then evaluated under von Mises and Tresca's failure criterion, with the PVC far surpassing the necessary factor of safety of 2, with both greater than 100.
To cover azimuthal rotation, as previously mentioned, an EML17 400-step motor is mounted to the base via a piece of aluminum sheet. This suspends the motor in place as it drives one of the planet gears. The custom fork for a system suspends the other 2 planet gears while still allowing them to rotate freely in place about their own vertical axes. The sun gear is supported on the threaded rod by a fender washer and a lock nut. The entire planetary gear system is housed within a 2 to 4 inch PVC expander connected to the central T of the support frame. The ring gear is epoxied into this expander. The thrust bearing interfaces with a fender washer directly below the engagement surface. The engagement surface is designed to be adhered within the interior of the central support frame T. This aids in the frame rotation about the threaded rod, reducing friction and stresses present. In previous iterations, the thrust bearing engaged directly with the interior surface of the PVC, but now our engagement surface decreases the torque required to turn the support frame and preserve the longevity of the subsystem. Now for some details on the planetary gear system. The central sun gear in the system is suspended on the threaded rod, supported axially below by a fender washer and a lock nut, and constrained above by our custom fork. The fork is fixed axially by another lock nut above it. A single key planet gear is driven by our 400-step motor. Since the other 2 planet gears are fixed and only allowed to rotate about their own vertical axes, this is a direct drive system. The ratio of this drive system is 4:1, which allows us to achieve a resolution of 0.11 degrees for the azimutation of our HELIOS set. This includes half-stepping our motor. The center distance between the gears was checked based on the constraint between the diameter of the sun gear, summed with double the diameter of the planet gears, having to equal the internal diameter of the ring gear. All gears have a diametrical pitch of 27 and a pressure angle of 20 degrees. The ring gear is adhered directly to the PVC support frame, so any rotation of the ring gear is equal to the rotation of the entire support frame. For more details on the rotation mechanism, I'll hand this back over to Ethan.
Rotation mechanism of the reflection surface is housed within the 4 outer cross connectors of the support frame. As in the azimuthal rotation mechanism, NEMA 17 stepper motors are used for reflector rotation, mounted to custom PMMA cylindrical mounts and adhered within the housing to prevent environmental damage. A custom bar stock motor adapter was used, sized to fit the interior diameter of the 3/4 inch rotation rods and bored to mate with the keyed motor shaft. An access hole is cut in the 4-way connectors to allow for the placement of 2 set screws securing the motor shaft to the adapter and the adapter to the rotation rod. Nylon sleeve bearings are used to radially support the rotation rods and lessen friction during rotation. They were implemented to replace radial ball bearings in a previous iteration of the design to avoid sand impacting rotation of the reflectors and reduce cost in a low-speed application. The subassembly is sealed with a 2-inch PVC plug and an O-ring to provide an environmental barrier for housed electronic components and allow access to the interior mounted motors if necessary for future maintenance or access to the wiring.
So let's now move on to the reflective surface subsystem. It comes together by cutting into the 3/4 inch PVC at a depth of half the diameter of the pipe and a width of 0.5 meters, where the reflective surface will rest. The reflective surface is then glued using epoxy resin to the back of the flat surface that was created by cutting the 3/4 inch PVC. This allows us to transfer the rotation directly from the stepper motor to the reflective surface. Our design uses soda lime glass with silver coating and is rated to have a reflectivity of 0.93. The module is composed of 4 identical reflective surfaces with dimensions of 0.5 meter by 0.5 meters, which gives us a reflective area of 1 meter squared. Now, because our design uses such a simple shape and has a flat surface, cleaning the reflective area should not take more than a few seconds for a full module. It's a matter of spraying some water or safe glass cleaning spray and wiping it down. Now, our design uses a frame that surrounds the reflective area, and at steep angles, the frame is bound to shade onto the reflectors. For that reason, we decided to use clear PVC that provides both the rigidity we need and allows most of the light to be transmitted through the PVC, 80% of it to be exact. Next, I will explain how the number of modules for a field was found. So the number of modules in a field to meet the demands of 1 megawatt power delivery to the receiver for at least an hour a day was found by first calculating the output power of a single module using an average solar irradiance of 1,361 watts per meter squared at an incidence angle of 45 degrees and optical efficiency of 0.93. A module area of 1 meter squared, and this gives us a value of 895 watts as the output power for one module. We then took into consideration the heat loss due to the radiation at the reflected surface. Using 5.67 times 10 to the negative 8 watts per meter squared kelvins to the 4th as the Stefan-Boltzmann constant, a surface temperature of 1,273 degrees Kelvin, and ignoring the surrounding temperature since the difference in temperature between the surface and the surroundings is too large for the surrounding temperature to have an effect in these calculations. Anyways, this resulted in a heat loss of 149 kilowatts. This means that our target output power is not 1 megawatt anymore, but rather 1.15 megawatts. Since we also needed a solar concentration of equivalent to 1,000 suns, we used the average solar irradiance constant and multiplied it by 1,000, which gave us a new target of 1.36 megawatts. Adding to that the heat loss found before, we obtained a final target of 1.51 megawatts of power needed. Dividing the desired output by the power generated by our module results in a field with 1,688 modules in order to meet both design demands. Now, Chloe will introduce how the system is controlled.
Our control system is composed of an ESP32 microcontroller that has both Wi-Fi and Bluetooth capabilities to send control signals to a central hub command computer to allow for automation of the heliostat's motion or rotation. The new 17 stepper motor drivers allow for half stepping, which reduces the resolution down from 0.9 degrees to 0.45 degrees for the reflector mirrors, and even lower for the azimuth rotation resolution to 0.11 degrees. The homing switches are used in the control system to send a signal to the microcontroller to reposition the mirror reflectors daily and to keep track of their axial position. The optical losses are 7% due to the reflectivity of the silver-coated mirrors, which results in a 67-watt heat loss for each module. Next, I'll discuss more details about the control box. So there are 5 motor drivers in the control box, and each of them dissipate 3 watts into the ambient air, which is 47.8 degrees Celsius. The scenario of a really hot summer day in Nevada was taken into consideration to assume the worst case scenario. This results in a total heat dissipation of 15 watts, which increases the air temperature inside of the control box to 103.1 degrees Celsius. Then to reduce the internal temperature inside the control box, holes were cut out into the plastic casing to allow for natural ventilation to the top for proper airflow. To find the heat loss due to ventilation, we first needed to calculate the air volume flow rate in the control box. And this value is dependent on the discharge coefficient, which is the ratio of actual discharge to the theoretical discharge of the fluid flow. It's also dependent on the height that the air travels and the temperature inside the box, which was elevated to 103.1 degrees, and the temperature outside the box, which is the ambient air of 47.8 degrees. And then the rate of heat loss due to the ventilation can then be determined, which turns out to be 1.3 watts. And therefore that results in a final reduced temperature of 98.3 degrees Celsius inside of the control box. And this final temperature is important to consider because it's well within the operating range of both the microcontroller and each of the 5 motor drivers. And it's also important to consider because this value is lower than the glass transition temperature of PMMA, which is 125 degrees, because the plastic casing of the control box is made from that material. And it's important to stay below the glass transition temperature because if the temperature were to go above that value, the polymer would then transition to a softer material and then have it change its molecular structure. Next, we'll discuss the key features of our design.
So our design uses an internal motor mount where the motor is mounted inside a 4-way PVC connector to protect it from the elements. And there's one set screw that attaches the rotation rod to the motor connector, and a second set screw attaches the motor shaft to the motor connector. Our design also uses a planetary gear system to rotate the support frame. And this was chosen to keep the gears internal to protect them from the elements, as well as to keep everything on the same axis. And on the right, our design also uses a thrust bearing that is held in place by a nut, which is used to engage the flat side of the bearing engagement piece. And this reduces stress as well as eases the rotation of the support frame about the threaded rod. So assembly time for our heliostat was calculated based on the Boothroyd and Dewhurst assembly time charts. And it was found that it would take 18.234 minutes to assemble the entire heliostat. And most of this time came from the support frame, which would take 13.62 seconds. And a lot of this came from applying PVC primer and glue to the different PVC parts. The control system was the second highest subsystem, which took about 3 minutes to assemble. And the base and reflective surface both would take less than a minute each to assemble.
So in terms of costs, the cost to fabricate one full prototype is $663.85. But when taking into consideration a full field, 1,688 modules are needed to obtain the necessarily solar concentration ratio. And that results in a total field cost of about $280,000. And that value includes manufacturing, labor cost, and the energy consumption to fabricate one module, which those values are $15.57, $41.70 for the assembly labor, and $1.52 for the energy consumption. And that the majority of our cost comes from off-the-shelf parts, which is preferable, and they comprise 87% of our material costs. After bulk pricing from ordering all the necessary parts to supply an entire field, our total cost per module was driven down to $164.80, as previously mentioned. So while the shipping cost for a bulk order is a little bit over $270, it does get divided out by the 1,688 modules, which then results in only 16 cents of shipping per module. So after a bulk order, we were able to drive the cost of materials for one module down by 84%.
The energy used to operate one of our heliostat modules for 1 month is approximately 5.85 kilowatt hours total. The energy consumed is split between the operation of the motors during daylight and the continual operation of the control system. Although the heliostat consumes 5.85 kilowatt hours per month, the energy generated is far greater at approximately 247.7 kilowatt hours. A conservative calculation was made for the energy generated by using a moderate solar concentration and accounting for heliostat efficiency. Using the retail value of 13.09 cents per kilowatt hour supplied by Gainesville Regional Utilities for commercial power, it costs about 77 cents to operate the heliostat for 1 month, or $1,300 for the field. And this does not include the cost for workers or the rest of the solar energy plant. Conservatively, the energy could be sold back to the grid at 4 cents per kilowatt hour, which means the field would generate about $16,400 per month, or $196,000 annually. Using these values, the net income for the field alone would be approximately $181,000 annually. In summary, our heliostat design should be chosen to be prototyped because it is sustainable, durable, and simple. Our design optimized the usage of parts and space to avoid excessive waste in a sustainable fashion. PVC and aluminum were utilized for environmental and corrosion resistance to support the desired 20-year lifespan of the product, while remaining highly durable. All things considered, our design was able to reach a factor of safety greater than 2 for all of our subsystems. And additionally, these parts allowed for a low cost of production. Utilizing 87% off-the-shelf parts allowed us to have a minimal manufacturing to achieve a simplistic design with a small footprint that effectively meets your needs. Finally, I'd like to address the advantages of a small-scale heliostat. Smaller modules increase the overall optical performance of the heliostat field by increasing the accuracy per module, thus generating a higher concentration ratio at the receiver. Smaller scale also decreases the wind stresses on the modules due to the smaller footprint, and additionally, the materials chosen do not need to be as strong compared to large-scale heliostats because the forces are much smaller. Our off-the-shelf parts are durable enough to resist the forces in the field, and this allows us to decrease the cost by utilizing plastic parts and by reducing the amount of required manufacturing. The small scale of our heliostat design allowed us to use a simple drive system, reduce maintenance costs, and increase durability. The main challenges we faced were the field design and the material cost. The layout of the field was complicated because the sun shifts position year-round, and the direction of the modules and optimal field shape was eventually determined by using the third-party software to compute the optimized position based on the sun's location. Additionally, the material cost was a constant challenge to keep low. We minimized costs to the best of our ability by using PVC as a support frame material and by keeping the amount of manufactured parts low. Through an iterative design process, we were able to continuously upgrade our module design. A few design changes made after the review were the choice to mount the motors internally and to increase the gear ratio of the planetary gears to further increase tracking accuracy. So that summarizes our heliostat modular design, and we hope it meets your needs adequately, and we thank you for listening. Are there any questions?
Okay, any questions from our panel?
Yeah, I'll go ahead and go. Will you guys go back to the cost slide, please?
Yes. This one?
Yes.
Okay.
So I may not be reading this correctly, and granted, it is, like 4 o'clock on a Thursday and my coffee has worn off. Do you guys have anywhere on here like what the cost per 100 meter or whatever, or the cost per meter was? Because I know that was one of the customer needs, if I remember correctly, was under $100 per meter, I believe.
Meter squared.
Meter squared, excuse me. I'm not an engineer. You got to work with me here.
Mm-hmm.
Yeah, that number was mentioned in the, I think, the product overview. If you want to go to slide 5, Alex.
Yep.
But yeah, it's the lowest we were able to drive the cost down was $164.80 per meter squared, and I think that includes materials, manufacturing, assembly labor, shipping, and the energy consumption to make the
Okay,
module.
so where it says bulk cost, that's for as if you're making a bajillion or however many you needed, 1,000 and something.
Our value, was 1,688 in the field, and that drove our price down a lot compared to the prototype.
Right, and I believe you mentioned, I saw a little footnote on the cost that said the manufacturing and assembly costs were included in one of them. I can't remember which one, correct?
That's correct, yes.
Okay, so as I kind of mentioned, I'm not an engineer, so I'm not looking at this from an engineering's brain. Like, I'm like, oh, that's a pretty piece of PVC standing on a pipe. That's, that's what I see, right? When I look at this, I'm like, okay, how much money am I going to spend? How much over my budget are they going? $164 over budget is not terrible, but the problem is you're probably presenting to somebody who their boss said $100 per meter squared. So now you've kind of put the onus on me that I have to go back to my boss and ask for more money. And that's not a position you want to put me in, because I'm not going to do it. I'm just going to say, no, sorry, no. So one of my main things I would say is take those manufacturing and assembly costs, separate them out, and really kind of dig into where you might be able to make that a little bit, I don't want to say cheaper, less expensive. Maybe where you can dig in there. Go back to the cost slide again, if you don't mind.
Absolutely.
There we go. OTS, modified raw materials, shipping. Yeah, so that's just, you don't have a lot of places to really cut back on your costs. At some point, you'll just have to figure it out. Welcome to being an engineer, figure it out. That's what I make the joke is all y'all do is solve problems. That's what being in engineering is solving problems. So just know, like me coming at this as an investor, I will get really, really hesitant when you're over that dollar amount. And the thing is, it's not that I may not want to give it to you. It's I may not physically have the money. I said I have $100 per square meter, and that's literally what I have. Go check my wallet, you know? So that's something to take into consideration. The other question is, or the other kind of side of that is, you can always go back and ask the customer, hey, $100 per square meter, is that a firm number, or, you know, do we have wiggle room with that? Because if they say that's a firm number and there's no way they can go around that, then sorry, you know, throw the product out the window. But they may come back and be like, well, we do have a little room. We can go up to a, you know, 175. Well, then, you know, hey, you said you could do 175. I got you down to 168, 164, whatever, you know? So always go back and ask the customer. I say if you have 10 customer needs, ask 20 questions. You know, you don't know what the customer wants, and it's very likely the customer doesn't know what the customer wants. So that's why you got to ask questions, not only to clarify it in your brain, but to get it clear in their brain and find out what are their priorities. Because you may not see the $100 limit as a high priority, but for them, that's priority number one. You know, they'll take extra safety risks or whatever. They probably won't take safety risks, but you know, they'll take risks in one of the other areas. So that's really my only thing. And that honestly is me just nitpicking because I need to find something to say. Overall, I'm very impressed with y'all's presentation. And left field, I want to say thank you all for dressing up. You all look very nice. All of your backgrounds are the same. You don't realize how much of an impact that really does have when you all look professional, when you all sound professional, when you're all sitting up straight, you're all presenting yourselves nicely. That gives me the impression that you have your act together. Whether or not you do or don't, I have no idea. But I have the impression that you have your act together because you look like it. So thank you for, you know, faking it till you make it if you have to. You all look very nice, and that really does reflect a lot in the presentation.
So to follow up for a second on what Julia was saying, I don't want to, you know, pour, what's the phrase, rain on your parade or salt in your tea, or I don't know. Anyway,
You go raining on my parade. I don't get many parades. I get like one parade a year. If you're gonna rain on it, I'm gonna cry.
Okay, then I won't.
No, I'm joking. Go ahead.
Well, so what I was going to say is, and to some extent, this is, you know, technology based and kind of beyond your control, but both with Ethan and Ryan, we had trouble hearing you guys. And it sounded like Ethan's microphone wasn't quite plugged in correctly. And Ryan, we're getting the sense that you were like far away from your microphone or in like a really big room. So we could barely hear you guys. You know, in the future, it might be good to like check the audio in advance to just see what you guys sound like to other group mates. Yeah, Dr. Chesney saying lean in, like before the presentation starts, because we were all trying to like help you without interrupting you. So we were all like dropping notes in chat, like get closer to the microphone, like check your microphone. So that just is a, you know, kind of the I guess the rain on Julia's parade a little bit.
If I can jump in on that, Dr. Trum, too. I know you guys have seen all the memes and everything. It's like, your microphone is off. You know, all the funny Zoom memes nowadays about how people can make jokes on Zoom on how, you know, people look silly because they're not doing something. Well, you can kind of see how that plays in here. So like Dr. Trum said, yeah, it was kind of hard to hear some of you guys. I understand sometimes technology hates us. Yay, believe me, technology always hates me, like all the time. But yeah, I kind of want to pair it with Dr. Trum said, that maybe make sure you get those worked out in advance. And you know, sometimes they're unavoidable, but like, you know, like we were saying, Ryan, I don't care if I got to see up your nose in order to hear you. Get right next to that screen, you know. Ethan, I don't know. I get a different computer. I don't know. I don't know what your issues was. I don't know technology, but you know, I agree that did kind of hinder it. There were some things that I just didn't hear. So while it sounded, I'm sure it sounded really pretty, I have no idea what you said.
Yeah, we apologize again for that inconvenience. Definitely a good point there, Dr. Traum. Was probably the last thing that we had to consider to run through in our presentation was the technology side of things.
Yeah, well, I can hear you perfectly now too. So whatever it was, it's been resolved. It might have just been proximity to the microphone. But yeah, just for future, when you're giving a big important presentation, like I mean, you guys got the idea. Just make sure that the technology is working. I don't know how many times I've had I wrote in chat, I've crashed 5 UF computers this year already, and it's, what is this, April? The guys in IT hate me because I touch a computer and it stops working, and I don't know why. So I'm right there. And yeah, Dr. Chesney's laughing because she's watched me do it. Yeah, so I'm right there with you guys. Technology is always like not my friend. So I get it. But anyway, okay. We beat this one to death. So any other comments from our panel?
Hi. Oh, sorry.
Yeah, you're
Oh,
okay. Go ahead,
Elise, please go.
Oh, hi, Elise from Cummins here. I really liked that you did a lot of different calculations, hand calculations. I thought that was really well done. And I thought you had some good animations and images as well. On your calculations, I think it could have helped to have some free body diagrams or cross sections to make it clear what area you're looking at and what forces you're considering. Just to have some visuals so you can see what you're considering there. But good job on those, especially like you went the next step and did a weld analysis, which was good. I had a question about the gears. Did you say it was like they were epoxied? Can we go back to the assembly slide? Yeah. So how were they?
So that outer ring is epoxy to that PVC expander. The sun gear is free to rotate about that central 3/8 threaded rod. 2 of the planet gears are suspended. Yeah, on this slide's a little better view. They're suspended in place by that fork, but they are free to rotate around their own axis. And then that last planet gear, which is keyed for the motor, that's what essentially drives the ring gear. And the sun and the other 2 planets just kind of spin in place.
Okay, so yeah, that main like the outer gear there, it's just epoxied on. So did you look at all of like the forces on that and the like adherence the forces on that, and what would it would take for that to shear?
We did some shear adhesive calcs between the outer surface of the ring and the inner surface of the PVC expander.
Okay, great.
To those if we have them.
Yeah, and so that thrust bearing is what is acting on the reflector PVC, right? On that engagement surface.
Yes, ma'am. That's so the whole support frame kind of can spin in a much, reduced friction, less stress. Because the PVC essentially comes down around the threaded rod, but the support frame rests at the very top on that thrust bearing.
Okay, so is that a metal on like plastic contact there?
Yeah, it's plastic fender washer, thrust bearing, and then a lock nut.
Okay, are you concerned about that wearing out at all?
We actually went through a redesign to kind of prevent it from the metal from biting into the PVC over, the 20-year period. That was one of the big redesigns. That's the whole reason that bearing engagement surface is up there. Originally, we didn't even have a bearing, but we wanted to prevent, obviously, the 3/8 threaded rod from interfacing at all with our PVC frame to kind of prevent that from biting. So that should be a lot less of a problem.
Okay, thanks.
Any more questions?
I I have maybe a little. First of all, let me say, I really like your layout, the work you did laying out the whole field, because that shows that you were really trying to dig down and address what your customers truly needed. So I would say that was excellent. My other questions are just kind of curiosity. So why did you choose planetary gear system?
It was almost a decision by necessity based on once we had our initial design and the shafts are off center. Planetary gear system seemed like the least amount of components and probably the simplest system to us.
Okay, and then I'm curious about clear PVC. How much pricier is it than just regular PVC?
We were able to find it for a very, very low bulk cost. It wasn't seemingly any more expensive.
Wow. Wow, neat. Do you have an idea about its refraction index and if that would make much of a difference?
So I'm not familiar with the refractance index of it, but it had 80% light transmittance through it.
Okay, so wow, I'm gonna have to get my hands on some of that. All right, thank you very much.
Thank you all.
Thank
And I'm gonna head out and head over to the next one.
All right. Yeah, I think actually we're probably at a good place to wrap up. Are there any other questions from the panel? Oh, we've got a celebration from Julia. No, okay, I think we're good. All right, so I'm gonna stop recording there.